recording. So I think we can start. Okay, so this is just with since it's a so. Okay, good. So this is going to be our third lecture, and today we are going to talk about. So we are going to finalize Dirac's equation. We are going to see the solutions of Dirac equation, and we are going to discuss them in what is called the poly-Dirac representation. That's typically the basis that is used to study the Dirac equation at first glance. It's convenient because it's already written in such a way that the solutions are easily obtained. But actually, the basis that is more convenient and that is used in research, let's say it's the Weil basis or the chiral basis that I briefly introduced. But that is something that you will learn on your own as like the first example sheet that I gave you to do at home. It's already in the web page, and you can download it. And it's 6 exercises that are going to be in a great part, sort of the same steps that we are going to do here, but to be done in the chiral basis. Not only, there is also one question which is still in the poly-Dirac basis or representation, but the others are in the chiral basis. And the idea, and I will repeat that once we get to the end of this section, is for you to learn and to understand exactly where these Weil spinors, the 2-component Weil spinors, are coming from, and for you to try to not confuse chirality and helicity. Here I will discuss a little bit of helicity, and then you will learn on your own what is chirality through the exercise. Basically, changing the basis, the thing becomes a lot easier to understand. So this is everyone that is enrolled in the course should send me those 1 week from now, let's say.
Oh, so we have to send you homework.
Yes, yeah. This is mandatory homework. You can do in whichever way you prefer. You can do in the computer and send it to me, like writing as I do these lectures in tablet. Or if you like, if you have time, you can do in LaTeX. If you want to write by hand, you can hand it to me. That's not going to be make a difference in terms of what is important. And this is something that I asked. The 6, yes. But the exercises is to follow the steps. Is to follow the steps that are here, but it's the purpose is a learning purpose, and it's in a way it's a guided exercise. But of course you have to think. But it's you will look into what was done in the lecture. And let me tell you that I was reading carefully this section of the notes that were in the web page, and I found a few things that. For example, chirality was written it's what a lot of books do. They talk about it, not chirality, helicity, and immediately say this is right-handed helicity, left-handed helicity. It's not wrong, but the left and right-handed of helicity is not what we usually say about right-handed and left-handed electrons, for example. This was confusing the notes, and I rewrote the thing. Talking about plus and minus helicity, and we will only going to talk about right and left when we talk about chirality, which, as I have said, it's something that you are going to learn through the exercises. Okay, but let's start. The first thing that it's important to recall is that we saw in the previous lecture that when you are in the proper frame of the particle, so when you have like the momentum of the particle 0, so you have that the Hamiltonian and the spin commute. So in fact, if you remember, and let me go to the other lecture, to the end of the other lecture. If you recall, these were the solutions, and there was degeneracy here. So two solutions with positive energy and two solutions with negative energy. And we lifted the degeneracy, so we distinguish between these two states with spin, because spin commutes with, we realize that spin is coming from this Clifford algebra automatically, so this gamma matrices, this encodes the spin. And we understood that through the commutation of spin and Hamiltonian, so these two operators are compatible. This is, if you remember from quantum mechanics, what are the definition of compatible operators. And you can distinguish the two states with the same energy because they have a different spin. So spin basically, so a complete set of commuting observables. In this case, it's S and H. S spin, H is the Hamiltonian. Right. So we had that. This was something that we got from the previous lecture. But now let's see what happens when we are not in the rest frame of the particle. So we are now going to do for the case where the particle is moving or we are in the laboratory frame. So we can rewrite the Hamiltonian, so we can recall the Hamiltonian, the Dirac Hamiltonian, which is given by this alpha dot p plus gamma naught m. This gamma naught is the beta that I introduced previously, but let me already call it gamma naught. Then we can rearrange this thing and we can multiply the Hamiltonian by h, and this becomes now that we have gamma dot p plus m. This is because gamma naught is the identity. And here let me then put the identity because we're talking about matrices. And also recall that the second thing to remember is that gamma is defined as gamma naught alpha. Right? So this is something that we have discussed in the previous lecture. So now we can just let's calculate the stationary states. And once again, if you remember, stationary states are the proper states of the Hamiltonian, are the eigenstates of the Hamiltonian, in other words. So we have this gamma naught h, and let me write a better h, gamma naught h, and then let's apply to a certain spinor, which is function of this momentum, and this is equal to gamma dot p plus m times identity. This is identity 4 by 4 u a alpha p. Great. Now these are matrices, and we are using. So here now we are using the Pauli-Dirac representation. Right, it's not very easy to write only capital letters. It takes a bit more time. Right, so this is the representation we are using. So let's use the gammas, the gamma matrices of this Pauli-Dirac representation, which in a block 2 by 2 block. Let me show you these matrices once again. Recall you what are these matrices. So they were already given here. So these are the chiral. Actually, these are the chiral, but actually there is here a sign change in the notes I give you, because this. I just say this side note. because of the exercise, for you to not get confused when you start doing the exercise. For this, the way these chiral matrices were defined here, this is correct. There is nothing wrong with this. But this puts the right-handed on the upper part of the spinor and the left-handed on the lower part. This is a convention. I prefer, this is the same thing as using the metric with minus plus 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 or plus minus minus minus. The alternative is flipping here some of the minus signs. And I wrote in the exercises exactly how I want you to use that. And this puts the left part in the upper side of the spinor and the right part on the lower side. This is just to warn you, for you to not get confused. But this definition is correct. And if you decide that you prefer to use this one, I will also not object because it doesn't change the physics. And I will never say that you've done something wrong if you don't change the physics, basically. Right. So, but these are the matrices that we are going to use. This is the Dirac representation. So the important thing to bear in mind is this minus here. So this is 1 minus. And also we have this minus sigma here in this lower component. So this means that when we come to the Dirac equation, we can rewrite this as follows. So matrix E, 1, 0, 0 minus E times identity. And this is why this poly-Dirac representation is quite useful, because you immediately see the two energies, the two eigenvalues here popping up, the plus and the minus energy. Can you see to the board? Or it's, I can try to adjust a little bit. Okay. So these UA and UV are two spinors, two component spinors. But once again, let me tell you that these are neither left nor right. You will find on your own as well. This is the first exercise. Exactly what is the chirality of these things, or if there is a defined chirality. This is something for you to. Sorry? Yes, UA and UV. Let me write this in a neater. Trying to write this neater. This is UA, and this is UB. Let's B. This is a B. Okay, and this is equal to, now on the other side, so you have the mass, so the mass is the diagonal part. Now we have the off diagonal part, which is minus sigma dot P and sigma dot P and M. And of course, this is
in one of the entries you have sigma times P, but I think it's minus on this side, on the left bottom side.
Here.
It's a minus.
It's a minus, yes. This is a minus. So if you at home, so if you don't understand a few things that I write, please, even for those that are online, please just let me know. Okay, right. So as I said, this UA and UB are two spinors. That is two component spinors. Now we can solve this. We can write this in two equations. In fact, we take two equations from here, and these two equations are, so from the first you have like E1 minus M. So this goes to the other side and takes a minus here. E1 minus M UA is going to be equal to, now this one here multiplies with this part here. So this is going to be sigma dot p u b. And on the other hand, because you have this minus sign here, and there is a minus sign coming from here, and there is a minus sign here, we can put all of them with plus signs. So let's already eliminate the minus signs. So we have E times identity plus M times identity UB. So this is now multiplying by UB. This is multiplying here, UB as well, equal to sigma dot P UA. Good. So we can replace the second equation on the first. So we can replace this equation on the first and get that UA is going to be equal to basically sigma dot P squared over, I will remove the identities now, E squared minus M squared UA. This is basically replacing, eliminating UB essentially. And now it's easy to note. So if you expand this this sigma, let me make a, this sigma dot P squared. If you expand this gives like sigma 1. I will write with some here to be quicker. Sigma I P I. Sorry, I'm not going to see. Right? So this is just the sum of the three momentum. Pi squared 0 0 squared. So this is simply P squared times identity, which allows one to rewrite again. So UA to be equal to P squared minus M squared UA. And you can immediately see, for this to hold, what is the condition? Basically, P squared has to be equal to E squared minus M squared. So once again, we get that E equal to plus or minus square root of P squared plus M squared, right? So once again, we have the positive and the negative energy solutions. So here we have just verified that indeed we have this the spectrum of positive and negative energy solutions. So we can write, because let's attribute to this the upper component, like the positive, and to the lower component the negative energy solution, and then we can write these two. We can then write right here the following. So something that I will call U plus. So this is a four spinner, U plus. A certain normalization constant. So we have not yet normalized the eigenstates, basically. And then this is the one that has UA, and let's replace in the bottom what is UB. And there we get, so looking here at UB, we can come here and see what is UB from here, or from, in fact, from here. No, let's use this one. We just need to be consistent, yes. And to get something that is sigma dot P over E plus M, that's the solution that was E plus M UA, and the negative energy solutions U minus P, which is going to be equal to the normalization constant. And now sigma dot P over E minus M UB, and here UB. So what we have is that here we have this E positive energy solution, and here we have the negative energy solution. Right. We can further expand this. So we know that UA and Osvaldo, yes, Osvaldo wants to ask a question.
If you take a particle and make it very, very massive,
Mm-hmm.
but then to infinity and dominates the energy.
What is the rest energy of the particle? It's the mass itself.
Yeah.
Right. So in that case, if it's very, very, so what you are saying is that what if the particle
non-zero p
with a non-zero p?
Yeah.
But that the thing is, if the mass is if the particle is very, very energetic, very massive, I'd say, and it has and you can approximate to the zero momentum, you simply have as if it was a rest, if it was at rest. That's typically what is done. But what is your point?
The negative energy solution. If the energy is essentially the rest mass, then that term explodes.
No, because it's negative, the energy.
Oh, right. Yeah,
Yes.
Yeah,
This is regular. Yes. Now I understand what's your point. Yes.
Right. Yeah.
But that's why it's written explicitly here. I could have written with some authors write the modulus and the minus. And actually, I think that the version that you have in that if you download the previous version of the notes in the website, I did like that, but I don't like that much that way. I revisited this.
Smart how we put down.
Yes, down you can see what's going to happen actually.
So we can know what you were saying at the beginning, that people, for example, m much larger than n, you have to be careful because the spinner is a function of the force vector itself.
The spinner is a function, yes.
And the energy is the volume of the force vector, so
yes.
you need to be careful.
Yes. Right. Now, what to do with these spinors? So, what are the eigenvectors of UA and UB? So, the eigenvectors. So, the most convenient way it's to attribute to this UA and UB the eigenvectors of the sigma 3 polymetrics. So. Let's give to U, A, B, the eigenvectors of sigma 3 polymatrix. That is K1, K minus 0, 1, and K plus 1, 0. Basically, this is for the spin minus and spin plus, or spin down and spin up. So we get that for E, for the positive energy solutions, we get U and let's call U and P. Now this is following the notation that we used previously, and this is a small u that we used previously for the case of the particle at rest. So U1, this is going to be a 4 spinner. So this is UA, so the spin up, it's going to be 1, 0, and now we have EZ over E plus M. You cannot see this. Yes. Let me just, I will try to move myself slightly away. I need also to move this up a little bit so that we can write. You can see now, right? And here we're going to have Px plus I Pz. This is something that you can do, sorry, Px, Py. Exactly. You can do it simply by expanding this sigma dot p. And let me write this is spin, so it's to occupy all of this. Right? I'm doing this slowly because this is so that you can follow all the steps. Because there are a few steps here. Now we write the second spinner. This is the opposite spin, let's say, 0, 1. And now here it's with minus. So Px minus I Py over E plus M. And Pz, I think it's positive, I know it's with a minus sign as well. So minus Pz E plus M. I verified all of this yesterday, so in principle this is correct. You can try it on your own or when you're doing your exercise. But I think I also confirm this with literature. It's like that. Now we have also for the negative energy solutions, we can write U3 equal. Now the upper components are going to have these p's. So Pz over E minus M, then Px plus I Py E minus M, and 1, 0. So this is the plus solution. And U4 equal to Px minus I Py over E minus M minus Pz over E minus M 0, 1. Right, so we have here the 4 solutions, but now there is something that we can use, and we can, as we have already discussed before a few times, is that we can identify the negative energy solutions as positive energy antiparticles. And we use, for the case of spinors, there is a convention to do this, and I'm forgetting to put the normalization constants everywhere. So there is this normalization constant, basically the normalization constant everywhere. We can use what is called this the Feynman Stukelberg convention. So let's use, so identify negative energy solutions, and I will write negative energy particle solutions with positive energy antiparticle solutions using the Feynman Stukelberg convention, which is, what is this convention? So this convention is doing the following, this one here. So basically we will call V1P, so this is a 1, V1P equal to U4 minus P, and this is the 4 vector. We're talking about the four vector P. And V2P, this is one possibility. This is not unique. You can add it, but this is the most convenient because you will see how the final solutions look like, and you'll easily identify the particle and antiparticle ones with this convention. U3 minus P. So this is the so-called Feynman Stukelberg convention. Let me see if so. 2 goes with 3, yes, and 1 goes with 4. Exactly. This is it. So essentially, it's doing so. You have a negative energy that you pass to positive energy, and you have a momentum that you pass to minus the momentum. This is essentially what we are doing. I think there are some authors that only change the momentum or only the energy. There are some other conventions. I'm afraid I've seen a few things like that in the past. But if you are already familiar with when you in QFT, and if you have already looked into Feynman diagrams and sort of things, sometimes you see for spinors Feynman rules with U's, sometimes you see with V's when you're talking about antiparticles, and this is because of this. So this is precisely what's going on here. So with this convention, the V2 or the V1P looks like. Actually, I will write first the V2 to make the mapping easier, because I will copy and paste the other one just for comparison. So V2P is going to be, so doing that, so we have PZ over E plus M. You can convince yourselves about this. We'll have an exercise to do that in another basis, but that's pretty much the same. Well, not the same. This will look, I warn you, the spinors will look a little bit different in the chiral basis or in the Weyl representation, let's say. But that's what everyone uses in real life, let's say. And V1P, which is going to be, and I'm forgetting the ends again, V1P is going to be Px minus IPy over E plus M. You see, Oswald, now it's already E plus M here. It's positive energy, and you recover the plus sign. Pz, so minus Pz, in fact, E plus M and 0, 1. Let me copy and paste the first two solutions. Oops, I will copy and paste more things about I want. Like that, so copy. Let's paste this. Let's paste here. just for comparison purposes. So you see, they look pretty much. So there is a, you look into the P's and E's, and they look similar when we are talking about the same spin. In fact, so here this is spin 1/2 here, spin 1/2. This is spin 1/2. This is spin minus 1/2. This is spin minus 1/2, and all of them have positive energy. And also, this is antiparticle. This one here is antiparticle. Particle. This is particle. This is again here antiparticle. Let me put the spin further now so that I have space to write antiparticle. And this is a particle solution. So you no longer have any degeneracy here. So either you have antiparticle with spin 1/2 or particle with spin 1/2, or you have antiparticle with spin minus 1/2 or antiparticle with spin or particle with spin minus 1/2. So there is no degeneracy here. And in fact, the wave function in general, you write the wave function using this Feynman-Stukelberg convention, has for particles, basically, for particles, you write like psi is equal to, so U12, so the solutions for particles, U12 P exponential minus I Px. These are for vectors here, and for antiparticles. So your solution, sorry, it's not U, now it's a V. It's V12 e to the I Px. So when you start doing QFT, you see these things. When you quantize the Dirac field, this you see this there. There is also the normalization. This is a trivial thing. Just the convention we use also for the normalization, or the normalization factor. Normalization factor n, use this thing like ui dagger uj equal to vi dagger vj, and it's normalized to 2 times the energy, and of course delta ij. Right, so just to be consistent, let me put the indices above ij. So we're using this. I'm not going to calculate this. It's a trivial thing, but you get that, and one of the possibilities is n equal to square root of e plus m. Plus m. So this is what you get out of the normalization conditions. You can, if you wish, you can try it yourself. Right, now, helicity. I started this lecture. I see that you are also writing a few things. I can wait a little bit. So online, is everything all right online? Are there any questions, anything you want to say? Please do not hesitate. If you want me to go back If you want to see something, you want me to scroll up the slides or something, just ask. So this is the advantage of not having, not writing in a whiteboard, is that I don't need to erase anything, and you can recover things that you have done since the first lecture. So I really like this.
It works surprisingly well.
Yes, it's also a surprise for me, I can tell you.
Because you are actually writing somewhere.
Exactly, and it remains for after lecture. If you don't have time to pass something, or if you want to pay attention, and if you realize, okay, I need to listen to this, but I will not be able to write, you know that at the end of the day you will be able to have the lectures to review. And also, it's less tiring for me. 3 hours standing and writing it. I was in the beginning, I was a bit like, oh.
Well, there's an interactive blackboard in the physics.
Mm-hmm.
Yeah, that actually does the same thing. You can also
You write on the board. Yeah, the thing is,
scroll back. It was a good idea. I don't know why.
yeah, it's really, at least for me, I'm finding it quite less tiring. The information is all there, and yeah, it works. It's
The changing of colors
Oh, that's
very
Awesome.
these things look really nice.
and it's more ecological,
Also,
a lot more ecological. Anyway, let's move on. Right. Yeah, but just to complement that, this is one of the good things that the pandemics brought, because I only realized this option when I was confronted with having to explain to my students, so the master students and PhD students, things, and then I bought this tablet to explain them things. But then I realized this can have a much better usage. Also for talks, I've been using this also for talks. So in the talk, I'm not writing, of course. I write everything before, but in some cases, it works.
you can like things in the man.
Yeah, because I have this thing here. I can do this sort of things, or I can do just with a normal pointer. Sometimes the pointer works better. Sometimes it's because this I can do this and that, and if I press like this, it keeps everything highlighted. Anyway, it looks like I'm trying to sell the program. Yes.
I looked into like writing solutions before I wrote paper. Writing solutions.
Yes. Yes.
There are some that have like a paper feel.
Yeah, it's you say a device to write. One is called Remarkable, I guess,
Remarkable.
or Remarkable.
Yeah,
I don't know I don't know how to pronounce. I don't remember how it was written. It's remarkable, right? It's remarkable. Yes. Anyway, let's now move on because the time is still limited. Right. Okay. So helicity. I started this lecture telling you that the spin and the Hamiltonian do not commute. Just for you to have trust me a little bit more, I just write here that SH is equal to
But only when the momentum is non-zero.
when the momentum is on zero. So this is when, let me put the condition here, the restriction that P different than zero. So in fact, what you see when you do the SH, you get the following block matrix, which is sigma, sigma and times sigma dot P, and here you get sigma times sigma dot P, sigma, yeah, there are no signs, and HS is equal to sigma dot P times sigma dot P times sigma and sigma. So can you tell already from here why doesn't it commute? So precisely. So the poly matrices, poly is a guy, so capital letter. The poly matrices don't commute. Commute is with double M. Therefore, SH also doesn't. Once again, when P is non-zero. Just to see this very briefly, if I write here, for example, let me highlight this one here, and there you have sigma I. Sorry, in terms of components, it's sigma I EI, and this is multiplied by this dot product, so it's sigma J PJ. Since there are, so for the gravity people, it's does it bother you not putting up and down indices here? They are summing. I'm just too lazy to write the summation, but I can write the summation. It's fine. So, so you have this, and of course I could just put the indices up and down. So on one side you have this.
That E you got there is what? The
basis, yes, that's the basis vector, yes. And then you have these other ones that you can write in a similar way. So Ij sigma. I will write with J. Just it doesn't matter, but I write with J, and then sigma I EI. And of course, the momentum and the sigmas do the commute, of course, Ij. But then you have here this sigma J, sigma I, Pj, EI. And you know that one of the things that you already know is that sigma I, sigma J equals to I epsilon Ij K sigma K. Once again, of course, this is a sum in K. Right. Sum in K. So this here, of course, this is all that you already replied, but this is different than sigma I, sigma J. And it's explicit, so it's very easy to see that these two matrices don't commute. So this is just to prove this this non-commutation. So in fact, this is what we have. But if you can write an operator, you know that you must have another operator that commutes with Hamiltonian, such that you leave this degeneracy, and you can find one that is compatible with the Hamiltonian. So a new operator compatible with the Hamiltonian that reads so let's write it something like H equals to 2. This is the definition. to S dot P.
This is written as a lowercase h.
Yes, yes, because it's to not confuse with the Hamiltonian.
Then I get confused with the Planck's constant.
Yes, that's right. But the Planck constant here. So if I do this, maybe it's explicit an operator. So for notation reasons, let's use hats in the H. Right. This is the helicity. This operator is called the helicity. So this is helicity. City operator. And this symbolizes or represents the projection. So this is the projection of the spin along the momentum direction. So this P modules of P is simply to normalize the so let's say the P direction pretty much to make it unitary. But it's irrelevant for the discussion. These models. But the physical meaning, and this is at the end of the day is what's important. This represents the projection of the spin along the momentum direction. And you can now see with this definition you can immediately write what is the helicity operator. So this helicity operator in a matrix form, it's diagonal because you can if you so P is a diagonal operator, and now you can just expand. You can convince yourself that this is right. That sigma dot P 0 0 sigma dot P. So things are starting to look great from the perspective of commuting when I talk about the following. So H is going to be then MC. Let me, by the way, write what is H once again. H is an identity sigma dot P and identity. Bear in mind that this is all in the Pauli Dirac representation of the gamma matrices. So M sigma, so the product is M sigma here, sorry, M sigma dot P, M sigma dot P, yes, exactly, P squared, M sigma dot P. So this is basically if you multiply these two matrices there, exactly, you have the sigma squared. So from here, I'm just confirming if it's squared. So this with this gives the P squared. And of course, this times this is this entry here. And you know, since the mass trivially commutes with the sigma matrices and P, of course, this is unquestionable. This is also equal to HH. So it's the exact same thing. So the mass just goes from one side, commutes without any troubles. So, of course, it follows from here that the helicity and the Hamiltonian commute. So these two operators are compatible. Also, what are the eigenvalues of the Ellicity operator? So it's an operator; it must have their eigenvalues. So if you square it, you get something like 4. I will already remove the 4's. So 1 over p squared sigma dot p squared 0, 0 sigma dot p squared, which is simply equal to, and that's why I wrote this p outside, this p here, because this is p squared, each of this. So this is going to be equal to 1, 0, 0, 1. So pretty much this is an identity. But what are the eigenvalues of this? The eigenvalues are plus or minus 1 here. This is a squared operator. This is a squared operator. So we can have both eigenvalues. We can have, so the eigenvalues, of H are then, and we can call them H plus or minus, which is equal to plus or minus 1. So this is the spectrum of H, the eigenvalues of H. So essentially what we are telling is that if you write the eigenvalue equation, so H U alpha P, this is equal to plus or minus U alpha P, provided that, of course, the spinors are eigenfunctions of H. Right. So doing this, we can do exactly this for the solutions that we had previously. So we already identified spin above, but and I said that leaves the degeneracy, and in fact we have those spins, but it is the helicity that is the actual operator that commutes with the Hamiltonian, and that's the one that we have to talk about. So to simplify our lives a little bit here, there is no need to be complicated. Let's just align P with the Z direction. So PZ and Z. This is just a simplification that I'm also suggesting you to do in the exercises. So in the exercise, I suggest you to do that. If you prefer not to do that, it's a different story, but I think it's pointless for you to complicate your life. So what we have is that H U1, now the modulus of P squared here is going to be Pz, and what we have then is exactly, so the eigenvalues plus or minus 1. So I think it's even pointless to write the Pz. I think you understand that already. But let me already write like this. So we have 1 minus 1, 1 minus 1, and then the rest 0. And now we apply it to U1. And to U1 it was 1, 0. Px and Py are 0, so there's another 0 entry here. Pz E. E plus M and 0. And this is equal to, so this, it's 1, this goes to 0, this keeps the same, this goes to 0. So it's the same, exact same eigenfunction. Z, so the same eigenstate. Not eigenfunction, eigenstate in this case. So this is a particle with positive helicity plus helicity and positive energy. And we can do this for the other ones. U2, this is going to be, this one I'm also going to do explicitly. So 1 minus 1, 1 minus 1, 0, 0. Now this is just up to right here, writing here the eigenvector, 0 and minus z e plus m. And now you note here that you have basically, so minus 1 goes with this, and this minus goes with this. So it clearly goes to minus the eigenfunction. Sorry, the eigenvector. So 0 minus 1, 0 is z over e plus m. So this is particle. This is a particle with negative helicity, with minus helicity, and positive energy. Without doing this explicitly, you can do the same for the other two. So you can do the same for HV1. And HV1, this will give you minus V1. So this is going to be particle, sorry, antiparticle, particle, negative helicity and positive energy. And finally, H V2 is going to be positive, so V2. And once again, this is an antiparticle, H is positive and E positive as well, so positive energy solution. Now, what about chirality? What about chirality? About chirality, which, bear in mind, it's different than helicity. So this is your exercise. This is your exercise to hand in. So today it's the 25th. Let's put on Friday to give you an extra day. You can hand in until the end of next week. Hand in until Friday. The 3rd. Right. Okay, so this exercise already counts already for the final evaluation, of course. Maybe there is something else that I will ask you to do, but not for this week, for another one. But let me, and I brought here a book just to follow this notation. Let me see that when you go to chiral spinors, when we are talking about spinors in the Weil spinors or spinors using the chiral basis, there are a few things that you will note that I will already anticipate for you to bear in mind. That, for example, you can write, I think you may have already heard about that you can write a Dirac spinor. So this is Dirac spinor is equal to a left-handed Weil spinor. Sorry, this is left-handed still for component plus a right-handed part. So this has a left and the right part. And what happens is that such that you have these are all four spinors here. It's the left projector let's projecting the left part of Dirac, and the right-handed is projecting the right part of the Dirac, where this PLR, and I think I write that in the lectures, in the exercises, is 1/2 1 plus or minus gamma 5, with gamma 5 given by, now this is the gamma 5 that I'm suggesting you to use, which is minus identity 0 0 identity. This is clearly to make the left part, the left spinner, the left vial spinner in the upper component of the Dirac spinner and the right in the bottom one. So this is written in the chiral, in the vial representation, or chiral. Vial.
So this is a chiral.
This is a vial or chiral representation.
Then we put the C under the N.
You can put the C here. It's fine. It's just to not move around with the C's and the. If you specify this is the representation I'm using, I will be happy enough. So this is not necessary if you specify in the beginning. And in fact, this is what, whenever I do anything research-wise, it's automatically this one that is used. But what are these psi L's and these psi R's? So just to give some information, so you can write this psi L, this left-handed Dirac spinner. These are all Dirac spinners here. Right, these are all Dirac spinners. And this psi L is written, so in this chiral basis, the convenience of the chiral basis or vial basis, so using the vial representation of the Dirac, of the gamma matrices, is that you can write this like that, psi alpha 0, so alpha equals to 1, 2, and you can write also psi r equal to 0 psi beta dot or alpha dot, doesn't matter, just let me write beta, with beta dot goes on 1, 2. So the dot is to tell you that alpha and the dotted and undotted indices transform differently under Lorentz transformations. In fact, these are two subgroups of the Lorentz group, let's say. One is the left Lorentz transformation, the other one is the right Lorentz transformations. So you cannot contract dotted and undotted indices. These are two different spaces, basically. So this is basically dotted and undotted indices. So dotted and dotted here, right? Also dot and dot this is this right better. Dotted indices represent or not represent, they denote or indicate that the two spinners, two types of spinners transform differently under the Lorentz group. Let me just make some notation adjustments here. This there are this big size that I will put here. This thing here. I'm putting this big size because the side that is outside is not the same side that is inside. So if you note in the exercises, I write this size with capital and the size that are inside with lowercase. So this is a big psi here. This is also a big psi. These are all big psis here. Let me see what else can I tell you about this. So that yeah, and then you can also. You will see this. You can also, and there are nice things that you can do with this when you have these dotted and undotted things. There is a metric for this space that is like alpha beta or epsilon alpha dot. Let me put with upper indices here. Okay, that's matter. Alpha dot beta dot. These ones these are written in terms of the Pauling matrices, of course, but they serve to raise and lower these indices. Raise and lower Lorentz indices. And they do that as follows. For example, if you have a certain spinor chi alpha, this is the same as epsilon alpha beta chi beta, or if you have some psi bar alpha dot, this is equal, and yes, typically if you write one up, you should write the other one down. Psi alpha dot bar, psi beta, and of course there is the alpha lacking here, epsilon, sorry, epsilon alpha beta alpha dot beta dot. So you can raise and lower indices, and you can even define something like the. And this is one of the exercises as well. You can define only, and the convention is typically to use only left-handed Weil spinors. So typically, one uses only left and left-handed Weil to spinors. For example, we can define what's called psi and chi. One of the things that happens is when you conjugate, and here the conjugation is with a bar. Once again, I will tell you that in the exercises it's defined there, so you will follow that. But when you conjugate the left-handed one, you transform it into a right-handed. Basically, the conjugation transforms left in right and right in left. So when you write something like, for example, psi L, psi R, you can put in a notation of purely left-handed as, for example, psi chi bar. And if we introduce the indices here, you can write the indices. So to be consistent, I wrote this ones like that, and then here you have beta dot. So this is the way we can typically define this basically these left spinors. And then there is also one final possibility here, which is you can define also Majorana spinors built out of Weil spinors. Majorana spinors. You can write, for example, psi m equal to, for example, psi alpha, psi bar alpha dot, or beta dot. Let me put beta to be consistent. Beta dot. So you see, these are two. What is the difference from this? Is a Dirac. This is a Dirac spinor. And this is a Majorana spinor. What is the major difference here that you can tell when you look into this? Basically, when you conjugate the Majorana spinor, you retrieve the same thing pretty much. So, what is the physical interpretation of this? Is that the particle and the antiparticle they are the same, and this happens for the cases of neutrinos. This is what happens in neutrinos essentially. Okay, let's neutrinos are not only neutrinos. There are more Majorana things in theory.
There's some
Yeah, there is something that was yeah, exactly, and there is also so there are for example in supersymmetry, not only there but in supersymmetry, the gauge genus, if you ever heard about gauge genus and the exenus. So gauge genus are the super partners of the gauge bosons. So they are fermions. They have spin 1/2. But they have the same internal symmetries. When we're talking about spin, we are talking about space-time symmetries. That's why all these relativity, special relativity discussions, these Lorentz transformations, because so far we've been talking about space-time only, essentially. But when we talk about internal symmetries, it's a different story. It's the gauge properties or global internal properties. It can also exists. And the gauge genus share the same internal symmetries as the gauge bosons, but they have the fermion. They are a fermion partner, so they have spin. So in terms of space-time, they transform differently. The gauge bosons are vectors, and the gauge genus are spinors. And you also have the same thing for scalars. So the Higgs is a scalar, so it doesn't have spin. But then there is a supersymmetry transformation, and this is something that we can briefly talk about the last 3 hours of the second course, or the last 6 hours. Let's see. If I will ask what you prefer, and I will try also to see with another course that is being done by Nuno Castro and Miguel Romão and Raul. And I will see what Miguel will talk about BSM. So I don't want to overlap with what he's going to talk about, unless there are a lot of you that are not doing these two modules.
What is the course? Experimental.
What is, Osvaldo?
Yeah, I don't think I have this.
That online. What is the course that the name of the course that Nuno is giving? Anybody knows?
I think it's experimental particle and astro particle.
Exactly. Maybe that's yeah. Maybe there are two modules. There one is the data analysis, and that's not the one, but there is one which is the particles and astral particles. And Miguel, so actually Miguel is a guy that he did a PhD in string theory, string phenomenology. So he knows a lot about DSM, and he's going to give a few, like 3 hours or so, or 1 hour and a half, I don't know, about BSM. So if you are enrolled in that course, I would recommend you to. But one of the possibilities is to talk a little bit about supersymmetry, just to understand how to transform spinors. Basically, spin from 0 to 1/2, from the 1 to 1/2. I will see, and I still have to decide and see what is the preference of most of you. Okay, since just to let's make a slight break, and we will restart in 10 minutes. Yes, and yeah, and that's it. So 10 minutes at 11:35 we start. And I need to recharge my energy. I will pause this. Okay, it's recording again. Good. So, just before going to Lagrangian formalism, let's just briefly, just in a very few lines, and in a very just look at the covariance of Dirac's equation, just as a short glance. One of the things that I'm planning to ask you to do also as a take-home exercise, not to end in next week, but I will formulate the exercise, if not in another example sheet, also I will formulate here in the lecture. But it's to prove, I'm thinking to do that, to prove the covariance, or like that the psi bar psi is a Lorentz invariant and not psi star psi, which is, it's not a very complicated thing, but requires you to go to books and to see how to show that, and that's like to stimulate your research capabilities to search for things. And I did that demonstration a decade ago or more, and you will revive my memory. So that's essentially the thing. Right, okay, but one part of that is like the covariance of the Dirac equation. It comes from there because we use the same type of objects. So covariance of Dirac's equation. It is going to be a quick discussion here. So once again, we start with Dirac's equation. Let me just zoom in a little bit, provided that everyone can see it online. Okay. All right. Gamma mu d nu minus m psi x equal to 0. Now we are going to pass it on to a frame where we write everything with primes, but for that we need to act the Lorentz transformations, as we have seen already a few times. But what we do now, let's just recall a few things, that like the mu is equal to the inverse of the Lorentz transformations, mu psi d nu prime. And also we make this transformation, and I will put indices here explicitly for a moment, as alpha and beta. This is a transformation on the fields, on the spinors. Psi beta equal to psi prime alpha. Of course, also the coordinates will transform. There is also transformation for the coordinates. I will omit this here, but they are also being transformed. Like there is a parameter a to act on the coordinates that bring them to x prime. I will omit for now. This is meant to be a quick demonstration here, just to arrive to a result that I think, if I'm not, my memory does not betray me, I think we'll use these results somewhere in Lagrangian formalism. Anyway, it's an interesting result on its own. So now, changing the frame, we put this del lambda minus 1 nu mu d prime mu minus m and s psi prime equal to 0. Now you can act. So now let's put the s gamma mu mu. And here I will already put s here. Now I'm omitting indices. I will already put so only the space-time, the four like the four space-time indices mu nu are not being omitted, but the spinor indices are. I will put s here already. D nu prime minus m s psi prime equal to 0. Now,
Capital S.
this is capital S on both sides, on both. Yeah, this is the same S. Let me capitalize it a little bit more. S and that S. Now they look similar. One of the things here that is to recall is that S acts on spinor space and lambda acts on coordinates. Thus, they commute. So this is why we can put S here in this place. So we can. That's why we commuted. We put S to the left of the lambda matrix. So now we can multiply on the left because this is a unitary operator also. So we have also that S minus 1 S is identity. So we can act on the left with the S minus 1, basically. S minus 1, and to be fast, I will simply copy and paste this here. Put this here. What happened?
I'm so jealous.
Jealous of? Yeah, if you want the remarkable, you could impress it. This is very useful. You don't have to write everything, and you can do all the steps. But it takes some time to get used to that. To be fair, it's not immediate. So I think there was some bracket here that showed up.
Yes, that's the next bracket. The next to the X.
The next, so you mean this small bracket here? Yeah. So let me erase the big one, which is going to. Oh, okay. Let's not be. It'll be easier to do this from the beginning. Okay, right. So now let's move this S inside this to here. So basically, we get I S minus 1 gamma mu S lambda mu the new prime minus m psi equal to 0. And let's say that this is equal to, and now there is one bracket also that should be added here, right? Now let's just say that this is equivalent or is equal to I gamma prime nu d nu prime minus m, all of this psi prime equal to 0. We are here, we are say forcing covariance.
Then it's not exactly a proof.
No, yeah, but this is only a glance at what is more. But there is
finding out what S.
Exactly. What is lacking here is what is S, and also looking at the coordinates. So this is a very, 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 because otherwise I would have no time to, and you will explore this a little bit more. So what happens is that this gamma nu has to be equal to transform in the following way. We know that the Dirac equation is in fact covariant, so that's why we are doing this way now. But this is not like a proof per se, let's say. But this can be, this is part of a proof. This is part of a proof, let's say, because what is left then to do is to look into S, expand S in terms of exponentials and factors, group factors, and so on, with the indices, and see that the things match together. Or we can also write this in like components. I mean, yes, components, in fact. So using indices explicitly. So this is an alpha beta matrix, and this is equal to S minus 1, and here it's alpha. Let's write rho gamma mu rho eta S eta, to contract that, beta, and now, so we already have alpha and beta indices here, and finally this lambda minus 1 mu. Let me put mu slightly. Okay, so this is for covariance. This has to be verified. This has to be realized. Right. I think you will come to this later on when you try to prove like that the psi bar psi is Lorentz invariant. You will need these results. But okay, this is it in terms of relativistic equations, and now we are going to change the page and we are going to Lagrangian formulation. So in fact, let me add a new. So Lagrangian formulation in classical theory. So this is basically where we are going to introduce several concepts. Now we are going to go in the direction of symmetries. Not yet today, but we are going in that direction. And then we are going, after that, we are going to break those symmetries. And that's where the Higgs mechanism is going to be introduced. But here we are already going to understand, to discuss a few things that will be important later on. But first, let's just recall a few things from classical mechanics itself. That you have this fundamental quantity in classical mechanics, which is a functional, which is the action. So let's recall the action. Recall the action as Q from classical mechanics. So this is a functional. I think you remember that a function picks up a number and transforms into a number. So a function is an application of R in R, whereas a functional, which is the case of this action, exactly, picks up a function, let's say. So this is, sorry, F, this is the space, so I need to be, so it picks up a function, so it transforms a function space, so something that is a function in a number. So here, I'm talking about real numbers, so let's stick to that in this, just this remembering. So, and we know how to define the action in classical mechanics. If you remember the action, so these Q are the generalized coordinates, and this is an integral over the time of a quantity, this L, which is the Lagrangian Q bar T. And the Lagrangian is no more, no less than the kinetic energy. So L Q bar T is no more, no less than the kinetic energy minus the potential energy. So these Q's are generalized coordinates. And also, of course, we use the notation Q dot is dq dt. So dots are, as usual, for time derivatives. So, and why is this introduction important? Because in field theory, we are going to use exactly the same principles. We're just going to change the dimensions. And there are a few things, in order to obtain the so-called Euler-Lagrange equations, there are a few things that we need to take into account. For example, we have 2 points, so 2 endpoints. So I guess you are guessing what I'm going to write here. So we have these 2 points. Let's call this is Q1, T1. So there is this coordinate Q1 at time T1. And at the end, the system evolves, or we are going to, we move to a second point whose coordinate is Q2, and we are there at time 2. We can take many paths, as you know. So we can take, I will use OS. We can take this path, all these possibilities. But there is only one. Here I will represent with a straight line. It doesn't have to be a straight line, of course, we'll see. Let me just put arrows here pointing that we are moving in that direction. But there is one, let's say, this path here, that is the optimal one, is the real one, is the one that basically minimizes this this action here. So this is what we call as typically Q real, which is a function of t, whereas the other ones are different. We can have, for example, this is path A, QA, T. This is QB, T, and so on. For example, just to have an intuition of this, if you, for example, if you throw a rock, this curves a parabola, because it starts with a lot of kinetic energy, it loses all of it to potential, and then converts again in kinetic energy, but this is always in such a way that this difference between the kinetic energy and the potential energy is minimized. If it was following a completely unnatural path going up and down, if something exoteric was happening, this would mean that at times it would have to have a lot of kinetic energy to compensate. If it goes on and suddenly goes steep up, it would require a lot of kinetic energy in that precise instant to make it possible. So this difference, kinetic energy minus potential energy, would not be minimized. And we know by intuition that that is not. We don't need a physics degree even. You can ask to a farmer working on the fields what would be the natural path, and he would understand intuitively this. So this is actually when I learned this, how I understood what is this of minimizing the action, in fact. But what we are doing is this difference, the kinetic energy minus the potential energy, is being minimized. And in fact, the trajectory, this green trajectory, is the one that in average, this has the least difference. So this is what I want to say. Has in average, the least difference between the kinetic energy and the potential energy, basically.
Or the most.
It's an extreme, yeah.
For example, in a sphere, the shortest distance point can be either this or the other way around.
Yes, and in that case, it's the most. Yes, so that's why this what we need to do is extremizing the action. It's not necessarily minimizing. That's a very good example. The example of the sphere, where so if you are on a globe, assuming that the Earth is a globe. If you go from one point to another one, you need to maximize this.
It has like a magnet of two attractive points and one repulsive in the middle. You would have the shortest one between attractive points, taking into account the potential would be something like that, right?
Yeah, can you ask again? I didn't understand.
Yeah, so if you had 2 points, and you wanted to move from point A to point B,
Yeah.
like a repulsive
Mm-hmm.
charge.
You have some repulsive force somewhere.
Yeah,
Yes.
it's just a magnetic monopole in the middle.
Yes. Yes. That's a dangerous thing to say.
Yeah, not go the least action to go from one point to the other because of that potential in the middle would be some way around it.
Yes. Yeah, because if
you
you
have the same symmetry
because it would have, if you want to cross this force, you would have to counteract that in such a way that it would not be natural. So it would not extremize, in fact, this difference, essentially. But that's also a good point. The sphere is more visual.
Yeah.
But that's
I was trying to think of the sphere
as a potential in a way.
The reason that we have that for the sphere is because we're confined to the sphere, right?
You know, that has to do with the form of the potential, I guess. It tells you.
The sphere is essentially like a potential.
It is, exactly. Precisely. Right, but now let's. So this was a nice discussion here, but let's now look into consider an infinitesimal shift of the real trajectory. So infinitesimal shift. When you do an infinitesimal shift, so we go from Q to Q prime. So this is Qi t plus delta Qit. And now we can do the variation of the action, which is like in functional analysis is the equivalent of derivation in a real in calculus, in real calculus. So this delta, let me not write S and delta in the same way. So this delta S is going to be this integral, because this is the definition of the action, and we are doing basically a difference between the action at 2 points using already the Lagrangian here. So this is qi prime q dot I prime, this is I t minus t1 to t2 dt L qi dot t. Right. And this is equal to t1 t2 dt L, and now it's using what is written there, qi t plus delta qi t. Let me remove the t's to make it less busy. So otherwise this will become very busy. So delta qi, so you know that there is this dependence on t, qi plus delta, this is not a g, delta qi dot t, and minus the other one. So let me already put both here, minus L qi q dot I t. Sorry?
Now you have an expansion at the first order on
Yeah. So, but in fact, so what you see from here, this is the definition, let's say, of the derivative. In this case, the functional derivative. So t2 dt, and so this is the functional derivative. So this is delta. So L is also this functional delta L qi qi dot t. Okay. And now you can use an analog to this total derivative, total differential. Let's say when we do calculus, you know this formula. So the dfxi, this is sum in I, the f the xi, the xi. So you use simply the same, the analog, but for functionals. And let me just no, let me keep this here to be aligned with the other group, with the other paper, with the other sheet above. So this is t1 t2 dt, and now we do just the expansion. So dl dqi delta qi plus dl dqi dot delta qi dot, right? And now this is you can you know that there is here so recall also that delta qi dot, this is d dt delta qi. So you can basically use the like this the derivation by parts, basically. Now t1 to t2 dt, and the same first the L dqi delta qi plus, or in this case, yeah, let's put the plus here, d dt, but now we are taking derivative of dl dqi dot qi, but you need to subtract minus the dt dl dqi dot delta qi, and I will use square brackets here just to distinguish. So these two. So from this here, let me highlight this one here. We are integrating the derivative, so this is trivial. For this one here, we already have, I will write in red actually. So this is already dl the qi dot delta qi between t1 and t2 plus integrating the rest t1 t2 dt, and now we have dl dqi delta qi minus the dt dl dqi dot dqi, and actually I can already put this dqi outside, but I will leave it for now. But there is now something that we have verified above, that all trajectories converge to this q1 and q2. Exactly. So all trajectories is converge at the endpoints. Q1, Q2, basically. So this means that this first one is 0. This is 0. And our delta S T1, T2, dt, and now I will put the delta q's outside, dl dqi minus d dt dl qi dot delta qi. And now using, in general, this was the discussion, using the principle of the stationary of the action, principle the stationary action. Basically, we demand that that is.
That's the same as Hamilton's principle, right?
Say again, Oswald, sorry.
That's the same as
Least action.
Yeah, this is the principle of least action. Exactly.
Hamilton's principle.
I don't know if it's the same as the Hamilton principle.
I thought that was. I think
It is related to that. I have to review my memory of classical mechanics, but I think it is related to that. At least you can, the Hamilton and the Lagrangian, Hamilton and Lagrangian, they are related. One is minus the potential energy, the other one is plus the potential. So it's like the Legendre transformation of one of the other, essentially. So the principle, I guess it goes there. But I don't remember the details.
My hands are cold, so I try to write as little as possible. So if I can shorten it 4 wards to 2, it's success.
Say again, sorry, but what's your point?
My hands are full. So,
Yes.
if I can shorten 4 wards to 2,
Ah, right.
it's a success.
Let's see. Nice. So, but we have this. Yeah. So you want the principle of least action? Yeah. It's Hamilton principle. Yes. 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 Yeah. Yeah. Exactly. Which is so from this we get that dl dqi minus d dt dl dqi dot equal to 0, and these are the Euler-Lagrange equations. So I will use throughout the lectures EL or Lagrange equations. Right. Of course.
Just to be clear.
Yes.
My understanding of it is that we can say this only because T1 and T2 are arbitrary, and so we could choose any trajectory, and because it always has to be 0, then the determined side has to be 0.
What we are doing is that we are fixing the we want to go from T1 to T or Q1 to Q2, and that's what we are fixing. We are fixing these two points. And what is the best trajectory to do that? That's
No, but the point is that just up top is where we see the integral.
here.
It's not obvious that would have to be. Well, if I say that's 0, it's not obvious that the determined side would have to be 0. It could just sum up to 0. If T1 and T2 are fixed and they're not arbitrary.
They are fixed, but they are arbitrary times.
Yeah, that's it. But we can only say this because they're arbitrary, right?
Yes, I think so.
This works for all T1 and T2.
I'm not sure if I completely understand your doubt.
So like if we were doing this derivation and we hadn't specified that T1 and T2 are arbitrary points, then we could make the inference from the first line to the Euler-Lagrange equations, right?
Right.
It only holds if T1 and T2 can be anything.
You can
So,
I understand.
Yeah, you can't do this step.
I mean, even if you
That's my understanding.
concrete times, for example, we going there from 1 second to 2 seconds, as long as the trajectories are fixed in these points, it doesn't matter if it's fixed, it's variable.
Yes, but
The trajectory itself, the
No,
street
it's not
is fixed.
it's about the derivation. It's just mathematical.
What you are saying is if the argument of this integral,
Yeah. So
if it's 0, it's 0 to start with.
Yeah.
It obeys. But if it's not, then you have these differences to be 0. That's the point. But it works in all. In any case, it works. That's the point.
Yeah.
Maybe you are seeing something else that is.
Yeah.
I'm not seeing exactly. I'm not saying that you are seeing something wrong, but at least I'm not reaching the.
There's something that we in our university class always. Well, I can accept it. It makes sense, but it always kind of bugged me a little that we didn't specify it, which is that if I'm doing this derivation, everything we've done so far mathematically, we could have done by specifying T1 equals 0 and T2 equals 1. Right?
Yes.
So we could, or anything like that.
Mm-hmm.
And if we do that, I think I can come up with some Lagrangian that whose integral from, or the derivation of the integral from 0 to 1 would be 0 without the actual equation there being 0.
Yes, but for a particular.
Yes, but that's the point. It's just I know it's just technical mathematical point.
Since you're here, we work with arbitrary time or a universal generalization. This is true for every time.
Yeah, exactly.
Yeah,
That's the thing.
It's long.
That thing, it
Mathematical.
it always works, no matter if you impose it to be already zero in the way that you are saying, or not. And there,
But can you extrapolate it if you don't specify it's arbitrary?
if I can extrapolate what the Lagrangian.
No, the Euler-Lagrange equations from the action.
Mhm.
Can you extrapolate the term has to be zero if the coordinate or if the space that you're integrating over, and later I suppose you'll do the forward.
Okay, well, I think I got there. But for example, imagine that t was 0 and t2
Yeah,
1.
you will get a
You have those complete values, but during this proof, you haven't used the assumptions that come with those numbers. You haven't used any special properties
No.
of 0 or 1. So your proof is valid for
Whatever.
every real number. I guess how much
Yeah.
you work to it.
Yeah, that's the thing. I don't know, Oswald, if you
No,
If you are satisfied.
It's no physical problem. It's not confusing. It's just a kind of a very technical point or linguistic almost that
Well,
yeah,
the broader way, maybe I'm not yet getting everything that you are saying, but in broader sense, because I look into this and I see that this works no matter what you do here.
yeah, which is, but it only works no matter what you do
If you impose that, so
if you allow yourself to do whatever.
I think you are putting this here. This is the principle.
Yeah.
The next
You see, this is the principle, and then from this principle, in general, you say this. But
you mean that
in general.
everything should be zero.
Exactly.
Why we set on the argument? I think he wants to understand what are the conditional reasons.
You mean so you are all of.
The point is just that all of it could be zero.
You mean if this delta qi is zero? But this is not possible because these are two different. This is non-zero.
Look, the point is the whole integral could be zero, and it's not obvious to me that because the whole integral is zero, the term inside has to be zero.
Mm-hmm.
Unless, of course, when we allow T1, when we say T1 to can be anything at all, then it generalizes to that because if T1 can be
Let's
anything.
say.
I think I got what it's saying. For example, when we have a second degree equation, a quadratic equation, we use the law of the little multiplicity. And we say, well, this must be zero or this must be zero. I think what he's asking is that how come we know that term inside the integral, when all of that equals zero, that term equals zero, and if we could integrate, okay.
Well, the issue is just, do you have to specifically say that this is?
I only see that as the only single possibility in the sense that you are integrating between two different times.
Yeah.
If it's between the same time, if it's the same time, it's zero to start with, of course. But the same time is also the delta q is zero. But
the same time is a particular case.
Exactly, it's a particular case that works. If it's not the same time, which is general, delta q is non-zero, unless you don't move. But if you don't move, it's the same as the Lagrangian does not have kinetic and don't have kinetic, and your potential you are already in the minimum of the potential. Let's say.
So at the start of the derivation, we said that the delta q was not zero.
Exactly, and that's also something that we said. So this is non-zero. So when you have this, when you have integration, the thing is this time integration between t1 and t2, and if the function that is here inside being integrated gives zero, it already obeys this. But
this integral with the arbitrary t1 can never be zero unless that term is
exactly that's how I see it.
It's completely impossible.
If this bit here is not zero, it will never be zero.
It can never be zero because
whatever
yes.
they're not equal.
that was discussed, I guess. If you can choose extreme way to go to zero without
So your point, let me see if I get your point. Your point.
My point, if I don't know what I don't know what Lagrangian is. I don't know what the Lagrange equations are.
Mhm.
Could I choose a Lagrangian and the specific T1 and T2?
So you are saying this.
I don't even have an unphysical Lagrangian. Like at this point, I don't even know what the Lagrangian is. Yeah, it's just some function that I call
Oops.
L. I imagine I could choose it so that between T1 and T2. Yeah.
You are saying this, and you want this to be 0.
Yeah, and I could choose some f that makes that be 0, while f isn't 0. And I'm saying that the arbitrary choice of T1 and T2, the fact that I impose that this must hold for all T1 and T2, is what then gives me.
So how can this integral be 0 if you have an integration between t and minus t, and if you are talking odd function, then that would be 0.
Yeah, and it wouldn't be 0.
But this is not. This is t. T1 is different than T2. It's not even minus.
Yeah.
So I don't see. So this is like, and T2 is bigger than T1.
So I guess. I think what you're saying is that
No. I think what's on my mind is what comes first. Like, is this 0 because of the properties of the Lagrangian, or does the Lagrangian have the properties it has because we impose the variation of the action to be 0?
We impose.
If we have the Lagrangian formulated as a physical Lagrangian, then I suppose I haven't tried, but I suppose that the Lagrangian are always going to be 0. Because that's part of the definition of what the Lagrangian is. But I guess that's, I suppose, the question. Do the equations come from the Lagrangian, or does the Lagrangian come from the fact that these equations must hold?
So I'm almost sure, but without certainty of proof, that this function has to be 0 for this to be 0. I'm just trying to understand it, an argument. I was trying to think in terms of just the area under a certain curve.
It's really not a physical question at all.
You go from one. So basically, if you think in one-dimensional terms, so you are integrating into.
I'm trying to derive this classical physics from scratch. I'm some sage in a cave who's never seen any other word, and I'm trying to derive it.
So you have this function, and what is the geometrical interpretation of a certain so you have a certain function, and this integral is going to be the area under this. Unless the function is 0, this is always going to be.
It's out of the area.
Exactly.
So the function could be negative at some point. But if it's an arbitrary function.
Yeah, but it can.
The thing from the line to
exactly, but that would be this. So something like this. And the area would be this thing here.
We make the condition that suit our convenience.
Yes, exactly. So
it's just when we use these, like I said.
yeah, but I don't see how can this not.
Because if I'm the sage in a cave and I just discovered mathematics and I'm trying to figure things out, and I come to this principle of least action, and I say, if things only happen this one way, that means that every deviation would have to, like, I have to be at a stationary point. Right? And I can figure that out just from reason. And from there, I can go to delta s equals 0. But I can do that without ever knowing what the Lagrangian is. I can use any function there, and the integral between like 0 and 1 of some function that does an s, right?
Yes.
It's like I can choose a function so that, or like the sign between 0 and 2pi.
But look, this is like you can think this in discrete terms. If this is the sum, this if you think this in terms of
I understand.
a series.
Yeah.
This is the sum of, so this should, if it's convergent or not, this is a different story. But if it should not be zero unless you make the function zero. This integral.
Yeah, but why shouldn't it?
Because this is basically you are summing bits of this f function between t1 and t2. This is a summation, essentially.
Professor,
And
that his problem is
sorry?
because I believe that his problem is because the function inside of the integral not necessarily is non-zero. So if you are summing a function that it's not positive definite, it might be the integral might be zero. You know.
Yes.
I believe that the problem, if you state that the Euler-Lagrange are the equations that externalize the action, it might be problematic. But I believe that you can show that the Euler-Lagrange are the solution that in fact minimize the action. So okay, you can have other solutions for this equation, but they won't be a global minimum, you know.
Yeah, the only
Yes.
that holds for
Yes.
all t's must follow this property.
Exactly. This is another property that perhaps is the missing point here too. So who was speaking? Sorry.
Etevaldo.
Etevaldo. Okay, Etevaldo. Yes. So I think Etevaldo made a good point here. But yeah, the thing is that the way you define this the Euler-Lagrange, well, the Lagrangian itself, it already can only work when this.
Yeah, but that's what was in my head.
Exactly. So this, if it's a positive definite function, this is clearly the case.
The Lagrangian comes, well, on a fundamental level, I'm thinking of it hierarchically, then these equations must come before the Lagrangian. Because you can imagine an action that's zero, and then you say, oh, for the variation of the action to be zero, then the function inside this integral must have this property of the Lagrange equation, and from there I can infer how Lagrangian.
But you define the action already with Lagrangian. They are connected. You cannot define the action without defining the Lagrangian. What you are thinking is if you don't even define the action, but if you don't even define the action, you don't even define this. So you are saying if it's a function, a generic function, and a generic S and a generic F here, if this property holds, if this is always true. So this is something that maybe we can remember. So you can look for your calculus and see if there is any property.
See, that's my worry, that I'm being circular.
Yeah, I think so.
I think we can say, for example, let S doesn't mean action or nothing now.
Yeah.
For example, let S be a function of the following form: integral of something.
Yes.
L, which is some function which doesn't matter.
Yeah.
If we say that the functional derivative of S equals 0, then the function that was trying to say
Yes.
integral must obey this.
Yes, that's the point. But what Osvaldo, I think now I'm getting what Osvaldo is, at least after a few minutes. Osvaldo is that if the integral itself, if the function is not 0, but the integral of the function vanishes. So if you are summing positive and negative, if the argument, so if the function, if the image of the function has positive and negative values, and when you sum all of this, they compensate to 0. Then, but that let's say that would. Yeah, because that would not be a 0 function. That would be a function that would be non-zero, and that would in principle give rise to that. The question here, so the points that are open here is if this say Euler-Lagrange, so this left-hand side of the Euler-Lagrange equations, if this is that positive definite, that's the first thing. If it's positive definite, this is clear that what is written here, the Lagrange equations are the only possibility. There is no other way around. And if it's not positive definite, so this is what we can check later on. I see. I now understand your.
I would imagine if it's not positive definite, then you have to use the argument. You can just
Well,
you have to use the argument that T1 and T2 are general, and if you integrate all overall possible, you have to prove that, I suppose, a function that's not positive definite does not have an integral between any arbitrary T1 and T2, or does not have an integral, or does have an integral between T1 and T2 that are arbitrary, that would be non-zero. I suppose you could go the opposite way. There's no way that an integral of a non-positive definite function is zero for all T1 and T2 unless the function is zero.
Yes.
So a priori, you are assuming that the equation of motion must be positive.
Yes.
Which makes sense because it's an energy, but
I mean,
Exactly.
You could make the following, or this S, the delta S equals zero. Then this implies that either the Euler-Lagrange equation equals zero or L equals zero. But we omit the other one because.
Well, not L equals zero.
well, no, because
It's the integral itself, L generic, but it
But I think by proving that the non-positive definite function, that if you can prove that a general function can only be true if
exactly. That's what.
zero, then you get a more general result and say
That's what none of us here at the moment have. So if this blue thing, if in this blue part here, if this would cancel out, if there is any, or if it doesn't, never happens.
Any function that would cancel out, there would be at least some combination of T1 and T2, so that at some T1, T2, the integral of that function wouldn't cancel out.
But that would be a particular case.
Yeah, but it's a particular case of breaking. That you can have. But if you're trying to say that this is a general general result, even
if you are equation.
yeah, exactly. So it needs to work for all those cases.
Yes.
Oh, but I get another problem.
Is it if it's the integral is zero and you don't have to and the Euler-Lagrange equation does not have to. I'm sure this should be that should have been thought already. But what Oswald is saying is, it would happen that the Euler-Lagrange equation would not necessarily have to hold.
That's exactly.
In that, but that's a particular case.
It would have to hold. I think, but I think you will get at it from the other way around, not by assuming Lagrangian has its property, but that the only general solution to the variation of S is zero is if the function that's inside it must follow the Lagrange equation. So we can't. I think the idea is to prove that the blue case cannot happen. Because there's no reason a priori that it should happen.
Yes.
I mean, we made no assumptions on that.
No, we haven't made any assumptions.
So, consequently, this must be no matter what.
Exactly. That's. But now the thing is exactly.
Particular case you mentioned must obey.
Yeah.
And this is the proof.
Yes.
Yeah.
But it's true. Do I assume that? Then it's true.
Exactly. Yeah, but it's of course it's a lot more understandable if this part here, if this bit here is positive definite, then we would have no doubts about this.
Yeah.
That's what actually we can all of us we can check this and discuss it next time. So what is behind this? That's a good point. That's a good point to have a deeper understanding. And if when we have a conclusion, I will add that to the notes actually. So that's a good point, Oswald. Okay, let's then keep on. This has delayed us a little bit, but it was an important discussion. It's not, so I never find this as a problem. Okay, so now, of course, you know from this that you can get like second Newton's law if you have, for example, Lagrangian. I will not derive that, but you know that if you have this well-known Lagrangian, so it's 1/2 m squared, sorry, mx dot squared minus a certain potential where x is q, then you get from this you get to f equal ma basically. So that's this is really the Lagrange equation. This is really pretty like the Lagrangian formalism. It's I really think that physics should be taught on this basis.
I never went back to Newton after I learned.
Exactly.
Never again.
Precisely. So now, what happens if we have more EQA, more degrees of freedom? I mean, a system of n particles, so n classical particles. So this is going to be so the Euler-Lagrange equations in field theory.
Just one question.
Yes.
When we go to Minkowski or other space-time, the coordinate we integrate over, it must be the proper time of the particle.
Let me think. It has to be. Yeah. Well, you can.
I mean, correct. In Newton, the proper time is actual coordinate.
Yes, but exactly, and this was
So
done.
in general, we must use the proper time.
Yeah, because here this was before special relativity.
Yes.
But the thing is that these equations these are invariant. If you make the Lorentz transformation of the things, it shouldn't change. But yeah, that's but this was done in Newton's time. Newton's time.
No, well, proper time.
So it's proper time from the exactly. No, yeah, sure. But now that there will be now for in field theory, it's a little bit different. So in fact, one of the things that classical fields result from a generalization yeah, to a continuum of n particles. And what is this n particle system? How does it look like? So the Lagrangian of this n particle system. Let's again, for example, if you look into this Lagrangian that lead us to Newton's second law, you can write this Lagrangian for n particles.